what I am looking forward to talking to you about over the next little bit is about, indeed, finding faults in Old Virginia. But I also want to give you a sense of what geologists do. This is a question I get a great deal. Why do you study geology? And if I was going to come up with a succinct answer to that, I think what I would sort of say is that I study geology because I like to climb mountains. And that may not be the best answer to offer up, but think about it. Mountains are these very interesting environments. Sometimes they're rugged, sometimes they're harsh, but invariably being in mountains, and I've always liked the idea of being in mountains. Now, why I moved to Williamsburg, we could ask that question, but in mountains, obviously one's confronted by the earth. Earth structures are there, rocks are typically there to be seen. And then as I've gotten older, you start to think about the mountain weather, a whole variety of things, and they're all centered on the earth. So part of my rationale, part of my interest for going into studying the earth had to do with thinking about truly the physical world around me. Now, I'm a structural geologist, and if I was going to put that down into sort of two nuggets, two little kernels, I would say I'm interested in understanding the architecture of the Earth's crust. How is it put together? And then also, what are the processes that actually change Earth materials? And I thought I would start with an example here. So this is a photograph from a beach, a cliff on a beach in Portugal. And hopefully, if you look closely, you get a sense that the strata that are exposed at the bottom are actually crumpled. You can see a series of layers that have actually been folded. So you might ask yourself, wow, these must be some dramatic processes that are capable of actually folding and buckling solid rock. These rocks are about 330 million years in age. Geologists refer to this as the Carboniferous period. But if you look a little more closely, you'll notice that these crumpled strata are actually overlain by a sequence of sandstones. In this instance, these sandstones are Jurassic in age, 210 million years old or so. And those strata are nearly horizontal. And my eye is immediately drawn to this boundary. We call this an angular unconformity. And for me, an angular unconformity is both profound and beautiful. And it's that way to me simply because enormous processes have been at work over time. And then we end up having yet more processes at work at some later time. So that's part of what I do as a structural geologist. Think about trying to understand structures like angular unconformities.
You see this kind of folds like that. What does it really make you think of? Folds up, upward folds. An anticline. So just spread out and take a look at the rock. Don't fall in the water. Yep.
What they are?
Yeah.
Okay, what do you think the white mineral is? It's hard, it doesn't have any cleavage. It's quartz, yeah. And then
rocks are wet because they've been rained on, so they're going to dry out and they're probably going to get weaker. And if you think of this happening through time, through years and years and years, you can start to develop a sense for how quickly these rocks are getting weaker.
Map. So I mapped the contact to see if it was a fold or a fault fold or if it was a erosional contact.
so the rock behind you and the one that we saw at Max, the stream outcrop, those are over 1 billion years old. So see if you can convince yourself which way is up. Up.
You got the basement, a sedimentary cover unit, and then your greenstones. But I just want to tell you, I've been doing field work with Chuck and Brent for like a long time. And doing summer field work is probably one of the most exciting and fun things you can ever do. Everything in the classroom really becomes really apparent how practical it is. You get a really practical application by being here. Doing summer field work and doing research, even as a sophomore, you can do that. And professors here are really willing to help you. And I'm really thankful for it.
A lot of people ask about geologic fieldwork. What is it like? How do you do it? Do you do it from the back of a truck? Well, typically, the fieldwork that we do, whether it's in Arizona or in Virginia, involves a lot of schlepping around. So each one of these colorful lines is a traverse that William & Mary geology students have walked through the Blue Ridge Mountains in Shenandoah National Park. And you can see that, well, here's the Skyline Drive, and there's some trails, but this doesn't look much like a trail. And we end up in a lot of crazy places. Well, back and forth, and that's because we need to find the outcrop. And when we find the outcrop, invariably, we spend a lot of time actually looking at it, observing it, trying to understand what is there. So here you can see the Alberine Dream Team modeling for us. They're looking at rocks. They're sitting on the ground writing notes, a whole variety of things. And we typically also measure the structure, the attitude that those rocks actually have. So that's a headshot of Charlie Shobe and Jeffrey Knox from last weekend's field trip. But if you look closely, they're actually using a compass. And that compass they can actually use to measure the orientation of rock structures, the orientation of a fault, or say the orientation of the linear structures in these rocks right here. And a lot of people ask, well, how much do you drill? And we do that sometimes. Here's a photograph, and this is in essence a chainsaw that's been modified to put a drill core on it. All right? It's pretty cool when you get to use it. You get to wear safety gear. You typically lubricate it with this pressurized water, and you end up drilling out 3 or 4 inch cores. It takes all day to do this kind of stuff. So oftentimes you have this interplay. Well, you can measure things, but if you want to drill, it's going to cost you time. And they're even bigger drills, but they cost even more money. And of course, we invariably come back to William & Mary, and we do things like look at rocks under the microscope. We analyze their chemistry, and we end up making most of our maps now really in a very digital way. All right? So that's sort of the process of how we do this. But the question some of you young students might have is, geologic fieldwork is fun? And I like to think it is. And in the Blue Ridge Mountains, it's often fun because we have a variety of creatures out there, all right, to enliven it. In Shenandoah National Park, bears are actually so common now that we just talk about how many bears you saw in a day. It was a 5-bear day. And as the summer drags on and they get more surly, it's a problem. But neither one of these are particularly much of a hazard in the field. In fact, I would argue that doing field work in most of eastern North America, the things that are most problematic are ticks and poison ivy. All right? Poison ivy oftentimes covers many outcrops. That's bad. And ticks are a chronic problem. Many of us have bitten many times. Tour de tick is sort of what happens in the summertime. So field work is fun. Take that from me. What I'm asking you to do here is to outline the geologic history of the rocks exposed here on the south side of Bell Island. So I want you to use rock names, like you wrote down, and then geologic action words. What are some geologic action words that might be appropriate? Deformed, intrusion, uplift. Well, boudinage is a thing, is it not? Ah, yeah, see, you can't trick you. All right, so every team gets one. And again, make sure you hang close to your partner. Surfaces like that, and the lineation is sitting here almost up horizontal. Right. What does that tell you about the fault?
That it's strike slip.
Bingo. And we're going to do C because there are lots of fractures that you can actually measure. All right? Right in here, we have people sitting on fractures, standing on fractures. A banding or a foliation is a planar feature, yeah? So we need to be able to visualize it in 3 dimensions when all we're getting is the intersection with the surface of the outcrop. So that's where your clipboard is going to be a very mighty handy friend. So I'm curious as to what these structures are and actually what the rocks are in them, okay? If you find that too crowded, some of you could even look over here. So this is outcrop B. Go ahead and go to it. Here.
The ones over there were so...
And really what I'm trying to get at is I think there's a banding here in this rock. And I'm going to call this a banding because when I stand up at this level, I can see the planar features in the rock. And you all can too, yeah? You see what I'm getting at? Instead of actually making this as a solid state, maybe this was some sort of a magmatic state. All right, you guys want to see one last spectacular thing here?
Yeah.
You don't see this everywhere. You don't see this many places. Come. This, to me, is worth the price of admission to Richmond. So take a look here. If you look at the whole outside of that, this very much looks like a very dark rock surrounded by the granitic material, and you might actually call that a what? A boudin. So what I'm up to is simply this. This is a nice part of the outcrop. It's actually been covered with a layer of silt from when the James River was probably last in flood. And with one water bottle in the hand, I'm trying to clean it off, make it wet, and then hopefully we can get everyone over here around this to look at it. So that's what I'm more or less up to. But if we look closely inside the boudin, what do we see? So let's all say this in unison. We've got boudins in boudins. All right, so that's very good. But anyway, that's very exciting because this is telling us, I think, a great deal about the processes that affected these rocks. What is actually coming through the audience right now are some William Mary geology students. In fact, they're William Mary structure and tectonics geology students. And they're handing out our little rock hors d'oeuvres. And I don't have enough for everybody, but hope you'll pass them around and share. All right, we do that a lot in geology, we share. But one of the other things I'd like you to look closely at, geologists are oftentimes accused of not dressing very well. And I think if you look at the William Mary Structure and Tectonics Research Group, you will come to a far different conclusion. Please pass those around. We're going to share these. And while they're doing that, I really would like to introduce you to the William Mary Structure and Tectonics Group. So this is the group of students that I work with. And year in and year out, I have really good crews of people. And a lot of what I'm going to talk about tonight are actually projects that William Mary students in geology have done as part of their senior thesis. So here you can see sort of the Rogues Gallery. And one of the things that happens, typically we work in the summertime doing field work. And it's not uncommon that they end up giving themselves names. So if we go back a few years, the Alberine Dream Team in 2011 and 12. Last summer, you can see that I got to hang around with the Gentlemen of Science and Leisure. Now you might ask yourself, why were we hanging around in a torrential downpour in central Virginia? And part of the class of 2013 in the field, getting ready to start the year, but they are unnamed yet. Perhaps suggestions will come from tonight. So hopefully you've gotten these samples. Again, pass them around, share. You don't have to hold on to one for too long. The college attorneys have asked that you not eat these rock samples, all right? In big trouble. So pass them around. See what you can see with them. In fact, these hors d'oeuvres, I think many of you might say, if there's enough light out there, that, well, some of them are colorful. Some might even be beautiful, right? You can sort of toggle them around. You can look at them. Different colors. Oftentimes, they're full of a variety of minerals in here. And we're going to talk about a few of these samples as the evening goes on. But from where you sit, I think you can hold one of these little cubes up. In fact, I've got some up here. And you'd get the sense that these are pretty static. You know, they are here. And one of the things that earth scientists study, and this is, for me, really why I do what I do, these rocks that you have in front of you that are so static right now, they actually have formed, and then, of course, been deformed by a variety of processes that are actually very, very dynamic. So the earth scientists are trying to understand that dynamism. And that is a dynamic set of processes that may happen not at a human time scale, but perhaps at a human time scale. So I hope when we're done in a bit that you'll have a little better appreciation, perhaps, for the fact that these are static in your hand, yet dynamic when we think about how they got that way. All right, gang, so what we've done over the past week is we have sawed up a lot of rocks that come from fault zones, fractured zones, a whole variety of places. And the idea is we're going to hand these out during the talk. And the whole idea behind this is that these are pleasant-looking cubes and rectangles of rock, and they're fairly static, right? You can use this as a paperweight. But what we spend our time in the structure group doing is thinking about all the dynamic processes that go into forming these fault rocks. And so part of my job is going to be to sort of illustrate the dynamism that we study in these rocks. So I'm hoping you guys will help me, one, hand them out, and then two, I think it might be a worthwhile discussion for us to have to plow through some of these and actually think about what kinds of things we see, maybe what I even should be talking about.
So we have very angular, brecciated sample.
Like varying class size.
We have fractures in this dominant clast back here.
They are little porphyroblasts of garnet that are through that whole thing. This is an L-tectonite. All right, so this rock, and what I'd like you to do right now is think about, can you find the lineation in this rock and can you figure out where the foliation is? All right, remember lineations are lines, foliations are planes. And some of these I think are really, it's very hard to find the planar structure in this, but you can very easily, I think, tease out the orientation of a lineation, right?
You can actually trace through these kind of biotite grains all the way around. So you can actually like see them here projecting out on this side, and you can see going through the foliation. And if you kind of look through and you kind of just follow some lines going along it, you can see different lineations of different minerals.
And as we deform things, we end up making basically an ellipsoid. And for these samples, this is actually from the Columbia Pluton. It's an Ordovician Pluton. I really think it's very clear that these ellipsoids are what shape? Prolate. So let's all make a prolate ellipsoid. Ah, yes. How many of you have one of these? How many of you got Play-Doh instead of a rock? All right, good. Now, I don't think the college attorneys want you to eat the Play-Doh either. But what I would like you to do is transform the sphere of Play-Doh that you have into a shape that looks a little more like this. All right, can you guys do that? Go ahead. And then pass it around. Show people your handiwork. So, I also don't think I should talk about what shape this actually ends up being. But what has happened in this instance, well, to make this shape, to go from a sphere to this sort of rod, if you want to say it scientifically, it's called a prolate ellipsoid. What you in essence have to do in some way, shape, and form, stretch the material in one direction while you're actually shortening it in the other two. And it turns out that's exactly what has happened to this rock up here. And if you take a look, you'll notice the streaks on the top face, on the side face, and if you look at it in the front face, it looks pretty much like a fine-grained granite. So something happened in the Earth's interior to actually draw this into a rod. And part of what we try to do is understand those processes. So I would argue that the rocks you have in front of you got that way by dynamic process. Okay, Virginia is riddled with faults. And I hope I'm not quoted in like the Richmond Times-Dispatch about that tomorrow morning. But if you look, these are just a sequence of the name faults, and there are others that are out there. Now, some of you may sit pretty and say, well, you know, we're here in Williamsburg. Doesn't look like we have very many faults over here in the eastern side of Virginia. And we reside in the coastal plain, which is a sequence of relatively young sedimentary layers. And it turns out many of the faults that we see in the Piedmont province are beneath our feet but buried. So one of the things we have to try to do is actually find those. Not an easy job. Rick Berquist, who's here, he works for the state of Virginia, has a drill rig, and he's trying to find faults here in eastern Virginia. So how does one find fault in a place that's covered by green, oftentimes outcrop poor? Well, one of the easiest ways to do that is to look for rocks that actually form inside fault zones. So this is an image that I've scanned from the textbook that I used in my structural geology class. And this is meant to be the Earth's surface. Here is a fault. And if you go deep and deep in the Earth's crust, it gets warmer. All right? The Earth's interior is considerably warmer than is at the surface. And this leads to a whole variety of different kinds of materials that can be produced when faults occur. So let's start up here, near the surface. If you break rocks up in a fault zone, you can end up producing this rock. And I suspect some of you actually have these chips. Maybe you put them in your pockets. Maybe you're still nibbling on them. But pull those suckers out right now. Pass them around. Share them. This is actually, we're going to have sort of a pronunciation lesson as well. This is a rock that geologists lovingly refer to as a breccia. And this, can you say it? Breccia. All right, very good. And this breccia is a rock that develops when the rocks are still cold and stiff. And the movement along a fault grinds and pulverizes this material. Sometimes it can be re-cemented back together. So if you look closely at these samples, I think what you're going to see is that there are fragments and more fragments and more fragments. And that happened in a fault zone. So that is, I think, quite a dynamic process. Now, how many of you have a rock that looks something like this? Go ahead, show it off. Yeah? Oh, bingo. Pass it around, maybe some others. Well, it turns out this rock has a far different texture. And this is another kind of fault rock. Yet this fault rock actually forms deep in the Earth's crust. The rock is so warm, it's actually capable of flowing down here at depth. And we refer to these rocks as mylonites. All right? And I find mylonites quite fascinating because you can't see them form at the surface. But when they are at the surface, we can learn a lot about what happens in the deep interior. So, the pronunciation game. I have one more fault rock I'd like to mention. And I want to mention this one simply because this is a fault rock that we have discovered since the Virginia earthquake in 2011. This is a rock known as a pseudo-tachylite. All right, say it. Pseudotachylite. And the way a pseudotachylite forms, I don't have enough of it to hand out. It's kind of rare. But what happens is if you have an earthquake that occurs, it generates frictional melting of rocks in and near the fault plane. So you're going to have a rock that was here one moment, an earthquake ticks off, the rock is violently melted, but not all of it melts, and you end up with little chunks and pieces of the rock around it. And then that quickly is injected into fractures and quenches into glass. And that's what we've got here. This is actually an exposure along the North Anna River, not very far from Kings Dominion. And what we have here is probably the best example I have ever seen of pseudotachylite in North America. And pseudotachylite forms only when you have large earthquakes. Now, we don't know the age of that earthquake, and that is, again, one of the other tasks. We need to date the age of this pseudotachylite. So I don't know that it's a problem about going back to Kings Dominion, but nevertheless, these are rocks that are glorious, and they speak to us of ancient earthquakes that must have occurred in the Virginia crust. This is a major fault zone here in the Piedmont. And what we're going to try to do is really examine some of the rocks in that fault zone, probably collect samples. So our whole purpose is to really get in here and collect some useful structure data, look for kinematics. So we're going to be thinking about rock type, fracture sets, can we figure out which cutting what, and so sort of both the brittle and the ductile story. We're in the Hylas zone. Cool. And, you know, this may be one of the major fault zones that jostled, sort of shuffled the deck of these blocks of rock in the Piedmont. If this is the foliation plane, and, you know, the rock's going to break that way, do you see any linear elements? Bingo. We can just flip the sucker and bail it that way. Okay. I think it is a very weathered granite. Long ride. Looks like we climbed about 200 meters. Okay. What time are we coming home? So look at this layer right down here below it. You guys say you saw some cross bedding?
Yeah, along here.
Yeah, that is garish cross bedding. Look at this. So that is a pebble, is it not? Mm-hmm. It looks like a granitic pebble. Mm-hmm. And this was a pebble rolling around 200 million years ago until we got our grubby little hands on it today and pulled it out of the outcrop. So that's one of the, to me, the aha moments of geology, this repetition of things that happen. So, you know, a pebble rolling down a stream bed, big deal, happens every day, right? Mm-hmm. Well, what we're doing here is we're sort of pulling them out of a rock that had it happen 200 million years ago. All right, I'm so excited I got to get a picture of this. So if we went to Charles County, Maryland, or King George, Virginia, and you drill a 300-foot hole, you would end up in rocks like that.
Oh, okay.
Yeah, so I think it was a pretty successful early spring float trip. The river sort of carried us with reasonable speed down, and there were some good outcrops. I learned a few things. There are a lot of things that I'm not really convinced I understand fully yet, but we got a box full of rocks to take back to Williamsburg. Okay, so let's pop into the Virginia Piedmont, and I'd like to give you a quick example about a fault zone called the Spotsylvania Fault Zone. And what was exciting about it was I was there last Friday. All right, my earth structure class was in the field, a busy time, and here they are. And what they're actually doing, they're touching the rocks. You see that? But they're doing more than that. They're actually trying to figure out how deformed these rocks are. So they're measuring the length of things that have been stretched. I think you can maybe look here and see things that have been folded. And if we do that at enough places, we can actually quantify how much deformation has actually occurred. The other thing that's exciting about these rocks is that the deformation is asymmetric. And what that means for a structural geologist is let's put arrows on it to show you which things actually moved. So in this instance, things moved that way. And if we go back to the early part of the 2000s, I had student Barbara Francis and Eleanor Eister who worked with me on trying to understand this Spotsylvania fault zone. And what they concluded was that, well, these rocks were highly deformed, strongly deformed. And this is sort of the kinematic model in 2 dimensions. The idea is to start with an original material, and you end up turning it into something that looks like that. Okay? We talk about strain and then vorticity. But it's considered to be bad form to talk about vorticity after dinner. Vorticity is, in essence, the amount of rotation relative to stretching that a material experiences. So take my word on that. But in essence, what happens here is that these rocks, this point is actually translated by deformation and shear to that location. So let's put this into a paleogeographic context. So our paleogeographic context falls into this map. Here's our Spotsylvania fault zone. And I'm going to mention two places in Virginia. Two places that aren't sort of high on anyone's list. One is George's Tavern. And as my students well know, there is no tavern left in George's Tavern. And that's on one side of the Spotsylvania zone. And then Goochland Courthouse, which is pretty self-explanatory. If we basically take this kinematic model and restore Goochland Courthouse to where it was prior to this fault, what we end up doing is taking Goochland Courthouse and moving it back to the northeast. Yeah, in essence, this fault zone transported this Goochland terrain from here to the southwest. So we've juxtaposed different blocks of crust here in Virginia. And if we want to scale this up, we can think about this at the scale of the Appalachian Mountains. So here are the Appalachian Mountains. Virginia is right here. Here's our offshore region. Put this in here as the coastal plain, because this buries many of the faults. Now, let's stick a big flag in the Blue Ridge. All right? And we're going to keep that anchored. We're going to keep that in the same place. And then let's put the Goochland terrain. And geologists use this word terrain, T-E-R-R-A-N-E, to refer to sort of a block of the Earth's crust, not just at the surface, but down deep. This is where it is today. And if we restore the motion on all of the faults that we see across the Piedmont, what that does is it requires us to translate Goochland somewhere back to the latitude of Rhode Island or Massachusetts. So we would posit that 350 million years ago, this block of crust that currently is in Virginia was perhaps 300 to 500 kilometers northeast of where we are. And today we find it here in this composite of things that are part of the crust that are in Virginia. So pause on that for a second. 300 to 500 kilometers of movement. I mean, that's a day's drive. And then the second thing, and I like this a great deal, because I think that this sort of speaks to the idea of old time. Bits of old Virginia originated in the Northeast. All right? So think about that. The capital of the Confederacy has rocks that probably originated in Rhode Island and Massachusetts. All right? So that is good work. And I would even argue that we can only get Goochland as far back as that latitude, but we don't really know where it came from prior to that. And in fact, it may be a chunk of some other continent, some other craton, Amazonia, the Congo, that was attached to North America in the north, and then later translated or slid along the edge of the continent to what we basically call today Virginia. I mean, the whole idea of traversing the Appalachians this weekend is to understand the history of the mountain belt, right? How did it get this way? And we also want to incorporate some of the other stuff we've done. Remember, we were at the Falls of the James, so we've seen the granitic rocks exposed there. We know something about their time depth history. We've talked about Mesozoic basins, and we're going to see a bunch of good stuff. So, shall we get started? We've just arrived at Hidden Rock Park here in Goochland County. And what the Earth Structure and Dynamics class is going to do, they're going to spend 20 minutes here looking at this rock, and I've asked them to answer and make a number of measurements about the rocks that are sort of directly underneath my feet. This is what you're interested in right here, okay? And then I guess I'm asking you here to make some estimate of how strained these rocks are. You want to take the distance between your part of the spectrum. Does anybody know what county we're in? We're in Goochland, and it turns out we are plopped in the middle of the Goochland terrain. And the Goochland terrain is this interesting block of rock in the Piedmont. One of the big questions is, what is the origin of the Goochland terrain? Is it a part of North America, or is it an exotic terrain? So if our model is correct, and it might not be correct, the Goochland terrain likely was shortened and slid along the Appalachians some 300 kilometers from where it started. So 300 kilometers to the northeast, that's that way. Puts us where? Connecticut. Boom. So we may well be standing on rocks that at some point were at the latitude of Connecticut but now are sort of down here in Dixie. All right, one down. How many more to go? Good question. Never here. You and your partners can get to work. I brought you to this part of the outcrop because there is plenty of good stuff to see right in here. And I'll also deliver up hand samples for you. So it's pretty clear the rock has a fabric, yeah?
Oh, yeah.
So the real trick is, what is the orientation of said fabric? So we got to find that on the outcrop in place. But think about this. So this is a quarry, right? It was an old quarry that they cut back to the hillside. So if you had a pencil and you lined it up parallel to said linear structure, you could more or less measure the trend and plunge, right?
Yeah.
Oh, bingo, bingo. So look at that. We are on the edge of this pink rock body. And what do you think a pink rock body is?
Ordovician granite.
An Ordovician granite, yeah. So, yeah, bingo. And this is called, not a very creative name, it's called the Columbia Pluton. All right? We don't see rocks of this age in the Goochland terrain. In fact, we're in a whole different terrain. We crossed a major shear zone, and this is the Chapawamsik terrain. Oh, yeah, it makes some people happy just saying the word Chapawamsik. But very distinctive belt of rocks here in the Piedmont. Okay? So some questions that we could walk away from here with, and you can talk about this in the ride. Why were there granites forming in the Piedmont 450 million years ago? Let's see if you guys collectively can come up with where you are, all right, and then pass that around. Locate yourself, and then we're going to march off to Outcrop A. This gives you a nice flavor for the character of much of the geology in the Piedmont, right? This is an outcrop that's not big enough for all 30 of us, but that's what we got. All right, so go to it. I'm going to try to deliver hand samples for everyone so they can look at this stuff, because I think you got to tell me what it is, right?
Take one too if you got.
Yeah?
Thank you.
Blocky kind of crystal, like right there.
Yep.
It's like a
Bingo.
blocky crystal shape.
Yeah, that's garnet. So good. We got garnet. They're also flaky ones too.
By its right.
If you guys want to see a little more of it in outcrop, there's a very fresh face right here. But angle the rock so that the sun is actually shining on this lovely structure right there, okay? Let's talk about what we saw, what we observed, and then we'll try to put it in a little bit of context. So what is it, gang? Yeah, we were looking at foliation. It's a metamorphic rock. It's got aligned minerals. And was that a primary structure or a secondary? Secondary structure. Let's think about this schist. Some of you might find this very exciting. So the belt of schist ends just north of Columbia. Can be traced all the way from here. We're about right here at this moment. And if you want to keep tracing this schist, you can keep tracing it, you can keep tracing it. And do you know where you end up? Quantico, Virginia. So we've seen 3 stops in the Piedmont today. Let's recount them very quickly. Hidden Rock Park. All right, that was in the Goochland terrain. We saw the Columbia Pluton, which is a pluton in the Chapawamsik terrain. And then we finished by looking at an exposure here of the Quantico schist, which is a metamorphic rock but younger than the Columbia Pluton. Well, thanks for a delightful afternoon in the Piedmont. You've been very patient with me, and I appreciate that. And I want to leave you with a few points, and then I think we take some questions and then have a reception. But one of the things I hope you can take away is that Virginia is riddled with faults. There are ancient faults, and I think we can speak to the fact that they are active faults as well. Virginia is this amalgamation of a variety of crustal blocks. Some of them we like to think of as exotic. All right, they may have come from Massachusetts, or even further afield. All right, bits of the Amazonian craton are probably parked in parts of the Blue Ridge Mountains. And that to me is this interesting deep story with Earth time. And I'd leave you with the point that we marine geologists have been and are going to continue to study structures like this because it's part of the exciting things that we do as geologists.